Kia ora koutou, it's Jaya here. I thought it would be a great idea if I create a little video to go through really the idea behind this notion of a metal transfer superhighway, this mad idea I've been waxing on about for a bunch of years and hopefully will get published in the next few months. I'm doing this because we've got a lot of people who have got engaged with a new program. It's called Next Generation Ore Towards Sustainable Mining for Regional Prosperity and Societal Resilience. And this particular idea underpins one of the first deliverables we're going to try and produce from this program. It's co-led with my colleague Chris Bumby from Robinson Research Institute at Victoria University, and deliverable 1 is led by David Dempsey, University of Canterbury, and this really underpins David's work. So I want to talk about this metal transfer superhighway in relation to New Zealand. And you can see New Zealand in here, and of course currently we're sitting on an active plate boundary, but once upon a time we were snuggled up next to Gondwana. And if you have a look at this diagram here, you can see Gondwana to the left. There is the plate boundary that would have been active during the Mesozoic. Inboard of that we had an active arc, and of course the roots of that remain. To the west we have material that has a close affinity to Gondwana accumulating in basins around that arc, and we call those Western Province rocks. Between or outboard of the arc, if you like, heading towards the subduction margin, we had a whole series of terrains that were brought in by the plate and sutured to what effectively was a backstop, a Gondwanan backstop, and we had terrain sutured onto that margin. And because the Gondwanan margin was relatively long and straight, these terrains, regardless of whether they came in with a bit of sideways motion or more directly into that margin, they ended up being long linear ribbon terrains separated in parallel ribbons, if you like, across what has now become the Mesozoic New Zealand basement. And overprinting them are some metamorphic overprints. The one that we're going to talk about quite a lot today is this Harst schist, and then we'll also talk a little bit about what has happened to these basement terrains through time. And the general idea is that we're going to look at the importance of the basement, and particularly the importance of some of these big lithospheric scale suture zones or tectonic overprints and metamorphic overprints as really important features in controlling the ore-forming hydrothermal systems that have developed from the late Cretaceous really to right now. If you look at this map on the right, you'll see these color-coded bands. This is showing you the basement rocks of New Zealand, and you can see that they're long ribbon terrains. They've been rotated into and offset by the Alpine Fault. That's a later feature, but in essence, if you unwrap them and put them on the boundary of Gondwana, you could see that they would have been long linear terrains. And in the back of them here would be the backstop, and that would be the boundary in through here between Gondwana and the accretionary prism. And everything you see off to the right really is the accretionary prism that would have formed on that margin. That rotation is what we call the New Zealand oricline, and it's an important feature when you actually start to look at the details of structural control on veins that might be hosting gold. If you come forward and we look at the next slide and have a look at where we actually have gold, some gold deposits are out here in the northwest, but I don't want to talk about those. They're older. Globe Progress is one of them, and they are Paleozoic orogenic gold deposits. The ones I want to focus on are the ones that run down the axis of New Zealand, and you have to remember that New Zealand really is an origin. It's been in compression and it's been under extension through time, but it remains an orogenic feature regardless of where you are along it. That's why it's above ground, above sea level at the moment. In the north, we've got the Coromandel volcanic zone, and associated with that are the Hauraki goldfields. And here's a beautiful example of sheeted veins that we see in these epithermal systems of the Hauraki goldfields. In the central North Island, we have active epithermal mineralisation occurring in the geothermal systems of the Topol volcanic zone. Champagne Pool is a classic example of that. And then way down the south, in the Otago area, we have the Otago goldfields forming really in the Haast schist, and here's an example of that, which is a fabulous deposit at Macraes. All of these are hard rock gold deposits, and I think they're wonderful markers of really fundamental geoscience processes, and that's hydrothermal fluid flow from depth to the accessible crust. So they're a marker. Gold is a marker, hydrothermal gold that is a marker of high flux fluid flow systems. If we look at the Otago goldfields, there are a couple of points I want to make here. You can see on the inset map where we are, so we're looking at this region here, and the Haast schist is actually marked out in grey here, so you can see how it's rotated into the Alpine fault, sheared out, stretched out, and we can track it up to the north here. If you were to unzip that offset, that would all line up nicely. In the Otago goldfields here, you're looking at, again, coloured stripes, and these coloured stripes are mapping out the different facies of the Haast schist, but also that boundary between where we go from Haast schist into the less metamorphosed Mesozoic basement rocks that form that accretionary wedge. And if you just look at those boundaries, they're all parallel to that fundamental basement terrain or New Zealand orocline ribbon terrain boundary, and it's marked out here by this line here, which shows you the connection with the contact with the Dun Mountain ophiolite belt, which is one of those basement marker terrains. If you take a cross section across the Otago goldfields, what you'll see, of course, is this incredible core complex, metamorphic core complex, where you've got the less metamorphosed material sloughing off the sides of an exhuming Haast schist core complex. And on the edges of that core complex, on the schist edges, that's the oldest gold. So that's the places like this up here in Macraes, and of course Doug Mackenzie's work suggested we should be finding stuff over here as well. And that developed at around, those gold deposits developed at around 145 to 135 million years ago. That was the first pulse of gold mineralization, and it was associated really with the inception of that Haast schist overprint. And then as the Haast schist was exhumed, it started to collapse, and you get these steeper vein sets occurring here in the centre, these extensional vein sets of gold, and that represents a pulse of mineralisation, a younger pulse at about 106 to 101 million years old. Just one thing to note, from a structural perspective, all of the veins that we're finding, or most of the major veins in the Otago goldfields, whether they are steep extensional veins in the axis of the exhuming schist, or if they're the more shallow or lower angle structures on the margin that are developing as thrusts, they're all parallel in strike to the actual margin. Parallel to the margin as it was when they were forming. So they're parallel to those metamorphic, those ribbon terrains, those Mesozoic ribbon terrains. If you look at the Hauraki goldfields, it's a slightly similar, same but different sort of a picture. Just to show you here, you're looking at the Coromandel, and if you ran up here, you'd find Auckland. In red here are some of the major faults that we see. This is the peninsula itself, and you can see it on this diagram here, which is a gravity map. You can see the peninsula cut off a bit at the top, down into that Hauraki rift. And on this picture, I'm also showing the Topol volcanic zone. Just look at that Hauraki rift for a moment, because it's a really important feature. It runs down through the Coromandel, separates it off this side here, which is really an uplifted block to this big extensional structure, this Hauraki rift that runs down and intersects the Topol volcanic zone. On this diagram over here, you can see that some of the active faults mimic that structure, and you can maybe see in some of the aeromagnetics that's been picked out that there are some features that are similar to that orientation that are running through the Coromandel block itself. But interestingly, the gold deposits here shown in yellow are tracking, they form structural corridors at high angle to that original first order inherited structure. And in fact, right down here in the topovolcanic zone, again, you can see the active faults are running up parallel to the active plate boundary, and you can see that the structure is really, the rifting structure here is really chopped up into a series of segments that are partitioned, most likely by structures that are parallel to that inherited first order structure. So up here we're a little different to Otago in that the main veins are forming at high angle to the original orientation of the ribbon terrains, and that's really a result of the fact that the active plate boundary today is at high angle to those terrain boundaries, because really of the development of the New Zealand orocline. We find that the gold mineralisation nonetheless is localised on the shoulder of one of those big features, or presumed features, which runs parallel to the Hauraki Rift, because the Hauraki Rift is parallel to every other terrain boundary that we can map in the region. So perhaps there's a first order control there, and I'll come back to that. If you map it out all on a major diagram, I was really amazed with this, and had a discussion in the early days when we first plotted this up and showed it to Dave Craw, and we just, our mouths gaped because it's just so obvious. Here is the picture of the active plate boundary coming in through here, and on this I've marked, thanks to Nick Mortimer's superb work, the marker terrains from New Zealand's Mesozoic basement terrains. And in red here you can see the roots of the old arc that was on the margin of Gondwana. It's been rotated into the Alpine fault, sheared apart. There's the other half of the rotation out through here, and then it rotates back into its main orientation. And then inboard of that you've got, in purple this time, the Dun Mountain ophiolite belt, which is also highly magnetic and can be tracked with great accuracy through the New Zealand continent. And then if you come in again, just go straight out to the blue at the boundary here. This is actually the toe of the old accretionary prism, or thereabouts, and it's dashed up through here, and you can see it's been rotated and sheared along this development of this Alpine fault. Inboard, we've got in green the dashed line that represents the Haas schist overprint of the basement terrains, and it's also parallel to those basement terrains, and we can map it out here just south of Lake Taupo, and it's parallel to those basement markers. And you can also see in here in yellow a little marker which is the Eskhead Mélange, and it is parallel to the basement terrain markers. There it is again, parallel to the basement terrain markers. We can't see it up in the north, but guess what? The gold deposits, the major gold districts of New Zealand up in Northland, around Puhi, in the Coromandel volcanic zone, the epithermal systems, in the topovolcanic zone, the active epithermal systems. There's a scattering of gold shows all along this Alpine fault through here, and then out in the Otago goldfields, there we have the orogenic systems, all lined up along the Haas schist overprint, or its inferred continuation to the north. Is it there? Is it localizing hydrothermal fluid flow beneath these epithermal systems? And if you have a look on this little picture I've made up over here, you go back to the Mesozoic time, you can see Gondwana in the grey here. You can see on top of that the sort of an example of someone's pick of what that plate margin might have looked like. In here you've got red, I'm showing you the position of the old arc, and then to the left of that are all the Western Province rocks, which have a very strong affinity to Gondwana. To the east of that we have what we call the Eastern Province rocks, which are really all of the rocks that are Mesozoic, that are the accreted terrains that developed in this accretionary prism on the margin of Gondwana. On top of that, I'll just show you where the Haas schist overprint is. There it is there. So we can map it in the south of the South Island. You can just see the boundary of the South Island there as it was back in Mesozoic times. Here's a bit of a sketch of the North Islands, not quite true on the east coast, but it gives you an idea of where it was. You can see the Haas schist coming up through here, and I'm speculating, does it continue to the north? And I think there's good reason to suggest that it does. This is what I mean by an accretionary prism. So you can imagine a bulldozer being Gondwana to the east of New Zealand. Here's the downgoing slab charging along the Proto-Pacific going underneath Gondwana. And the bulldozer has a bit of a acts as a backstop to this wedge, and in front of that all of the shed material off Gondwana comes into this accretionary prism and forms a big pile of sand in front of the bulldozer. All of the material that's coming in on the downgoing slab builds out this big wedge and forms this huge accretionary prism. If you know anything about wedge theory, then you may know that the shape of these wedges has a particular cross-sectional profile. They like to have a particular angle between that top surface and that downgoing surface, and that is a critical angle, and it's defined by a few different parameters. But the key thing to know is that if that wedge gets too long and too thin, it becomes internally unstable, and it deforms in order to get back to its preferred shape. And its preferred shape is one where this downgoing slab can slide quite happily, this can slide across the top of it, and no internal deformation happens. But if it's too long and too thin, it doesn't like it. Uwe Ring wrote a fabulous paper back in 2019 that discussed this wedge, and it discussed in particular the Eskhead mélange. And what Uwe noted was that if you step across the Eskhead mélange, and I'm showing the position of it out here in this map, here it is in blue, going down through here, there's the Eskhead mélange where we can map it out. If you step across it, you lose 15 million years of stratigraphy. It's gone. From one side to the other, the stratigraphy is gone. And Uwe asked a very sensible question: what's happened to it? And he looked at that question from the perspective of wedge theory, and he concluded that the missing material was underplated beneath the wedge. And he suggested that given the age of the Eskhead stratigraphy, you're missing stratigraphy from 145 to 130 million years. That's 15 million years of stratigraphy. He suggested that was underplated at the time, around about the time of 135 million years ago. And he suggested, with some good reason, that that produced the harsh schist developed under here. And in the vicinity of that, of course, is in the south, would be under Central Otago. So just to show you on this map, in green here is the position of the Dun Mountain ophiolite belt, which we're treating as the backstop on the bulldozer. The harsh schist shown here starting to develop under Otago, and we can track that, gets shared along the Alpine Fault. You can track it into the south here, and the Eskhead mélange in blue. In red, of course, we've got the magmatic arc beneath the old Gondwanan arc, and then the overprinted by the active plate boundary. Of course, a critical question here is that if that Eskhead mélange signals underplated material, then there's an interesting and provocative notion. And if you look at the shape of the North Island, what I've done here is just showing you in white the outline of the east coast as it was, as we think it was, based on various lines of evidence, at about the time the Coromandel volcanic zone was kicking off. Now, if the Eskhead mélange had been developed earlier, then the Eskhead mélange would have existed in this vicinity, i.e. outboard of the Coromandel. If it was subducted underneath the overriding plate, one could assume or presume that it may be subducted under here, under the Hauraki Rift. And therefore, that provokes an interesting notion that there is a single structural belt that's of great interest along along the New Zealand origin. Oops. Why I'm interested in the harsh schist is that in the Macraes area, we know that it has got a lot of graphite in it, and that graphite is partly to do with provenance, so incoming material that is graphite rich, and partly to do with the fact that it is hydrothermally deposited. Now that means that the more you put hydrothermal fluid through the system, the more you are going to weaken the structures in the rock through which you're putting that fluid, because you're getting a feedback mechanism. So it's a very, very interesting feature, and I'm interested to know whether that graphite is pervasive throughout the karst schist, and if it is, does that give us a weakening mechanism that makes the karst schist a particularly favourable localizing feature, particularly where it might abut harder rock that might focus, because of that rheological contrast, focus deformation and therefore focus fluid flow. If you look at what's gone on during time and you come forward in time, then there's a very interesting feature, or a very interesting event took place on the plate margin. So here's our accretionary prism. At this point, what has happened is that a large igneous province, which is called the Hikurangi Plateau, has come into the plate margin and impacted it at around 108 million years ago. And I'm showing that up on this diagram up here, where you can see this Hikurangi Plateau has a bit of a dolphin's beak that's impacted that long Gondwanan margin, and here are the basement markers so that you can see where they are. It's impacted it at about this time. And as a result of that, the overriding plate goes into extension, and I'm showing that by the bulldozer reversing. And what happens then is this overriding plate starts to collapse. And as a result of that, we see exhumation of the core complex as this starts to undergo extension, and we see the karst schist starting to be exhumed, which is really interesting because if you look at this map here, and we're going to jump into it in a little bit more detail, you can see the gold deposits of the South Island, and you can see gold deposits on the margin of the schist belt. That's where that rheological contrast is quite strong between weak karst schist and stronger surrounding rock. And then we can see gold deposits right through the interior of Otago. Again, just to show you a little point about this before we move on, that impact of that Hikurangi Plateau has focused strain along the margin of, along its margin, and it has sheared out these basement terrains and sheared out that karst schist, which if it's a weak structure is a really good localizing mechanism for developing and focusing strain along the Alpine Fault. If you look at how the karst schist has evolved through time and space, here's a great picture by Mortensen. Actually originally developed this, the making and unroofing of the karst schist in southern New Zealand. And you're just looking at time on the bottom axis, you're looking at gold mineralization style and metamorphism on the vertical axis, and we'll just follow two paths. We'll follow what happens to the lower green schist facies host rocks on the margin of the karst schist belt, and you can see that through time we're coming up from green schist facies, going through the brittle ductile transition. At about this time you're seeing McRae's develop, and then as that continues to be exhumed, you can see Glenorchy coming in. If you look at the interior of the karst schist, so this is the core of it, you're looking at higher metamorphic grade rocks getting exhumed later and under extensional conditions in the core of the schist. And there we're developing the second suite of gold mineralization in through here. I'm just going to map onto that some of those key features. So you've got the Esqued Mélange occurring at about this time, and that's the gap in the stratigraphy, and the underplating occurring late in the gap, which is coinciding with gold mineralization through on the flanks of the schist belt. And then later you get the Hikurangi Plateau impact occurring, and that's coinciding with the overriding plate being thrown into extension, exhumation of the schist as a core complex, and development of steep extensional gold hosting veins in the interior of the schist belt. Just to show you that and emphasize the point, we've gone from being a convergent margin to an extensional margin as a result of that large igneous plateau impact, at least in the south. What does that mean for the gold deposits? Well, if you look through here, based on Pitcairn's excellent work, he's mapped out shows of gold in white, Pleistocene gold. Coming down, we can see in the dark colour, we can see the Miocene gold coming into the Mesozoic gold, into the main part of the Otago schist belt. So you can see there's an age control here. There's the gold deposits and shows are getting younger, even to the point where we've got now this warm springs coming in through on the active plate margin. And you can see the harsh schist shown there, and it's getting strung out along the alpine fault, and it's actually overprinted by a younger metamorphic overprint, which is called the alpine schist, but I haven't got time to go into that in this talk. If you jump to the epithermal systems of the North Island, start first on this inset. This is excellent work by Hannu Seebeck, who demonstrated very nicely, based on volcanic products here shown by the circles, that the orientation of the arc has been relatively the same for the last 16 million years, parallel to the current boundary, but the age of the volcanism has shifted to the southeast in association with rollback of the subducting slab. So 16 million years ago through the Coromandel, coming to about 8 million years ago, and down to the current day here through the Topol volcanic zone. Jumping onto this gravity map, which is showing you some big holes in the central North Island where the rifting associated with Topol volcanic zone occurs, and also where we've had some big eruptions of caldera forming eruptions. On this you can see fault orientations here in black. You can see the orientations of the rifts through the Topol volcanic zone that are chopped up into rift segments through here. I'm showing you the geothermal systems in red. There's some triangles here which show you andesites that have been dated, and of course the gold deposits in the circles with the vein orientations that are parallel to the active plate margin through here. And again, you can see colour coding. You can see that the gold deposits are mimicking the age, as you would expect, of the magmatism as it's shifting to the southeast. If you put that on a little cross section, this is what it looks like. I'm starting way up here in the top of the Coromandel. I'm just running a profile down through to the southeast side of the Topol volcanic zone, because this is really just all one evolving arc system through time. Normally you'd run a profile like this perpendicular to the arc, but I'm running it in this orientation because I can get the data. So from time on the vertical axis to distance to the current active eastern margin of the Topol volcanic zone, we're tracking arc migration with the triangles. That's the dates of the andesites. In behind the arc migration, you can see the rhyolites following but are lagging behind, and then you see the basalts coming through in part really when they get an opportunity, but very much associated with opportunistic extrusion of those basalts, because they really don't get to the top very often. You can see a couple of porphyry style deposits there in the triangles, and you can see the gold tracking and following that arc migration. But here there is a big pulse in gold mineralization. The size of the circle indicates the size of the deposit, and of course this is around when Waihi comes into activation. That arc migrates quite happily till we get to about 5 to 2 million years old, and then it jumps into its current orientation and position along the active arc. What was going on in time? Well, back 25 million years ago, we were starting to rip apart the alpine fault and starting to reset the active plate boundary through New Zealand. And here is our old friend, the Hikurangi Plateau, which impacted the plate margin at the time of the Otago goldfield development. And now what's happening is it's forming a pivot point on that plate margin, and it starts to rotate into the active plate boundary as it's developing in New Zealand. And you can see here at about 15 million years ago, we're starting to get the Coromandel volcanic zone forming along that arc. And this Hikurangi Plateau is trying to rotate into and under the overriding plate. So it's impacting it. It's buoyant. It doesn't want to go down the gurgler. And what the overriding plate does, as it always does, is it's thrown into extension and it's trying to break apart as a result of this impact, which is really locking the system up. Interestingly, the Hauraki Rift opens up. Now, the Hauraki Rift is not nicely oriented to be an extension or a zone of extension in this overriding plate, but nonetheless it opens. And that tells us that it's opening because it is exploiting a very, very weak feature. And that then comes back to the question of whether it's exploiting something like a harsh schist correlative underneath the Hauraki Rift. As time goes on and we're heating this overriding crust because of the arc, the deformation starts to prioritise along the topal volcanic zone, and so the Hauraki Rift, although it's still active, is not the main locus of extension anymore. Just to put that into time for you, Hauraki impact is about 10 million years ago. We need to do a bit more work on that. And then, of course, we have the opening of the Hauraki Rift. Again, we need to do more work on that. But there's a smoking gun there that's worth exploring. Just a quick note, I won't dwell on this too much, but I'm just showing you this map of the North Island junction magnetic anomaly. That's the Dun Mountain ophiolite belt, a major basement terrain marker from the Mesozoic, showing you the Hauraki Rift parallel to that. It rotates into the topal volcanic zone, and then of course presumably the major structures are running a little bit more parallel to the junction magnetic anomaly in the south. Up in the north, you can see that the veins forming in the epithermal systems and the faults forming in the topal volcanic zone, at least in this area, are at high angle to the basement terrain fabric. And that's interesting because it chops the system up into blocks. And that's different, remember, to the south where the veins are forming parallel to those basement terrain markers. If you have a quick look at why that's important, if you jump out to the western platform and you look at seismic reflection data, you can look through, like Superman, you can look through the stratigraphy to the deep-seated faults shown here in grey. This is obviously a basement, an inherited basement fabric. And as you come up section, the younger structures in black start to swing off that deep-seated structure. They're linked to it, but they swing off it to run parallel to the arc. Now, why is it important is because the deepest pipes of permeability are at these corners, where the younger structures that continue up section are routed onto the deeper structures that remain active in oblique motion at depth. If you think about it, in a rifting environment, the brittle ductile transition will shallow as rifting progresses, and if you've got structures that are within the basement that are localizing deformation up section, then they continue to influence the transfer of fluid from depth to surface. They become shear zones in the lower crust, and so they're a way of impregnating the upper crust with material from the ductile regime. They have this long inherited role to play. So they might move material from a mass and fluids from the lower crust into the upper crust, and then as these structures bifurcate and rotate into the active arc, of course the best place to get the juiciest hydrothermal system is right at the corners that I showed you before. So just to sum up then, if you look at the whole zone, this harsh schist, and whether it continues to the north or not, there's some interesting features that have happened. We've had major tectonic events at the plate boundary, Esqued Mélange underplating coinciding with the first phase of mineralization in Otago, the large igneous province impact coinciding with the second phase, and then that impact again potentially coinciding with the third major phase of mineralization in the Coromandel, all strung out along the harsh schist, and maybe it's correlative, unexhumed correlative to the north. Down here in the south, of course, when the veins formed, everything was parallel. You would call that coaxial strain if you're a structural geologist. But by the time we had mineralization in the north occurring, you've got these arcs crossing that inherited fabric, and you're getting much more slicing and dicing and chopping up and structural complexity in the vein systems. So I'll finish there and hopefully have sparked some enthusiasm and thoughts and ideas to test into the future. Thanks very much.